Hi guys, welcome back to this video on HYSYS. So in the last video we've actually compared how two plug flow reactors actually differ between the diabatic and adiabatic configurations. Okay, hope you can hear me better. Anyway, yeah, we have actually compared, how the yields of a diabatic and the adiabatic reactor actually differ. You can see that, well, for one thing, the yield of methanol actually increases, and the selectivity of methanol also increases because you see there's less carbon monoxide produced in the diabatic case. So that's generally a good thing. Yep, that's generally a good thing. So we kind of want to keep it that way. I mean, for the extra costs you're putting out, you're actually generating more high pressure steam, and you're also making more product. So overall, it looks like a very good deal. And of course, if you know about copper, zinc, and alumina catalysts, you know that their operating temperature is about 280. And with our reactor here, we can see that the top, the top temperature is about 284, which is kind of acceptable, I suppose. Of course, here the temperature is like 286, which is slightly higher than what we have wanted. But on the whole, the diabatic reactor seems better in comparison. So we'll want to start looking at our diabatic reactor, and we'll want to stick with it. And of course, in the last video also, quickly we've went through how to calculate the heat transfer coefficients. So for the QA, the Q equals the UA times LMTD. We have actually talked about the wall heat transfer coefficient and the heat capacity and etc. All these and the Nusselt number will be used to calculate some kind of energy flow. And we have to make sure this outside steam molar flow rate kind of closely matches this molar flow rate here. So this is at 8920, this is at 8945, so it's pretty close enough. Yeah, because we are using a condensed high pressure steam as the coolant. So what HYSYS is doing is estimating the amount of energy that is able to be transferred using this high pressure steam as a high pressure steam generation as a cooling mechanism. So it's calculated that based on what we have keyed in, and of course based on the molar flow and of course the latent heat as well. That's just an estimate, yeah. And we have arrived at a value about 765, and that's what we were doing in the past two videos. In case it wasn't clear, I hope it's clear. Thanks for your patience in my yammering. So okay, without further ado, let's just start on the heat exchanger aspects. So as usual, we'll press our F4, our trusty F4 key. So let's press F4, and we'll pull in a new heat exchanger. I'm just going to call this the simple heat exchanger. Simple heat exchanger. Okay, for good reason, because this basically is a simple model of a heat exchanger. It's not the rigorous kind, but we'll go to that in a bit. So for the shell and tube side fluid package, we'll want the pink Robinson. Okay, and we'll just click close. And the reactor effluent we know will need to be cooled. So let's just drag it to one side. And this reactor reactants will need to be preheated from some preheated feed. Okay, so the reactor reactants will be the cooled version, the cooler version of these reactor reactants will be this stream 1, which I'll just name as reactor reactants to heat. Okay, so what we are doing now is some heat integration. Yep. So we are going to pull out another stream just by pressing Control and pulling out. So this new stream number 1 is the cooled reactor effluent. So I'm just going to write cooled reactor effluent. And for this simple heat exchanger, we are going to look at the parameters tab, and we're going to use the simple weighted heat exchanger model, and we're just going to specify a pressure drop of about 100 kilopascal per side. And it says it's under specified, which is fine because we haven't specified any kind of temperature. So let's actually specify the inlet temperature of this reactor reactants to heat. So I'm just going to put about 50 degrees C. That's just an estimate. And we can see that our entire HYSYS actually turned blue, which means that this is a solved case. So you can see that the reactor reactants to heat has been like heated from 50 degrees C all the way to 250 degrees C, and the reactor effluent is cooled from about 280 degrees C to about 125 degrees C, and that is calculated for us by the heat exchanger. So simple heat exchangers are relatively easy to do. The challenge usually comes when we try to turn this into a rigorous model. And rigorous models, as the name suggests, are a lot more challenging to do in HYSYS, so that will be the main focus of this video. So for that, we'll just want to clone this whole setup so that in case we mess it up, we kind of have a backup spare copy. So as you can see on the right here, this fella has been cloned, and we want to name this as a rigourous heat exchanger, and the rest I'll just leave it be. And HYSYS has this ability to turn simple heat exchangers into a rigorous model, and all you have to do is just go to design and go to connections, and once you have this green bar saying OK here, meaning the heat exchanger is solved, you can start writing the size heat exchanger. So you can just press that, and you can just use the auto size function and just press convert. Of course, there's a way you can actually size it using sort of you can size it using what do you call that? Yeah, you can size it interactively, but we will not discuss it in this video. So now that the heat exchanger has been sized, it says that EDR, rigorous calculations, will set outlet stream conditions. So they ask you whether you want to override the existing outlet stream specification to avoid over-specification. The usual case is, of course, we press yes. And now we realize that the whole heat exchanger system has just not been solved. So what do we do from now? Well, there are two things that we need. So what's basically happening now is that, well, let me open this heat transfer workbook. Just Excel to help calculate. So what's happening now is that HYSYS is trying to calculate some kind of Q value, which is the heat transfer rate, and then multiply into and that will be calculated by the U and the A and the log mean temperature difference. So it's going to do that iteratively, and you need to give it some kind of input parameters. So there are 3 input parameters you need at least. So what has been fixed is this rigorous heat exchanger. It kind of gives you the estimate of this A value, which you see here, the area. The area has been fixed already, so you can't change it anymore once you rigorously size. So this A is fixed. So what you need is the 2 inlet stream conditions, and then the 2 outlet stream conditions will be calculated by HYSYS. So that is what the whole commotion was about previously. So to make it to define the inlet stream conditions, we'll need to do some simple things. First thing, we'll need this reactor reactants to heat. So we'll need this stream I'm selecting here to be dark blue. So all we need to do is just define from stream, and we'll look at reactor reactants to heat, and just press OK. And that's part 1. And now part 2, we'll need this part to be blue as well, this inlet stream. And well, the most convenient way is to use a recycle stream, because the recycle stream can, use the, it can put an initial gas basically. So I'll just name this the reactor effluent RCY. That's a recycle for heat exchanger. So that's what I'll name this. So that's the gas. Now I'll just name this as HEN RCY. HEN being a short form for heat exchanger network, and I'll just put RCY because it's a recycle. So, oops, I'll need to write that, and I'll just put continue. All right, so that kind of solves it, partially, of course. We haven't actually done anything yet, so I'm just going to make it a little nicer to look at. So I'm just, for that, I use the number keypad 3 to actually turn this around. Okay, I'm just pressing the number keypad 3 just a few times, and it just does that. Okay, so we need an initial gas for this reactor effluent stream, so we are just going to use this. You'll put the initial gas parameters in this stream here. I'm clicking, so I just put a define from stream, and I'll look at reactor effluent. I'll just put OK, and then the thing should start running. So it's running now to see whether it can iterate. So just wait for it to iterate. Just drink some water first. So it seems to be iterating, and the outlet stream temperature is just changing a lot, and it's dropped dramatically from about 280 degrees C to about 177 degrees C. So basically the stream is overcooled, in other words, and it says maximum iterations reached, meaning this thing hasn't converged yet, so you have to press continue. But we kind of already know that this result isn't exactly what we want, because we want the outlet temperature to be about 279.6. And what do we do then? So basically, I think we kind of got to stop this thing from running. So once it reaches the maximum iterations again, I'm just going to like stop it. Then, well, the obvious thing is to, if this thing is there's not enough heat in the system, I'm going to increase this temperature for this one, maybe to about 160. So let's put this fella at about 160, and the cooled reactor effluent will be at 186. So okay, we'll see whether it works. Okay, so the outlet stream should be about 186.5, where the cooled reactor effluent is. So let's just try that. 186, oh no, 160. And there you go. The thing is going to iterate again. So the temperature is rising. As you can see, the outlet stream temperature has gone back up to 280 degrees C. And it's gone back up a little high, in fact. Well, we'll just let the recycle stream do its job. And look, now it's converged again. So at 160 degrees C, it kind of does this thing. So apparently our outlet temperature has increased to about 284. So that's just, I suppose, cause of the way the recycle stream actually iterates itself. But this actually the inlet stream should be lowered to about 250 degrees C. Okay, so we want to let it match this reactor reactance thingy, so we'll make it lower a bit, 150. So we are taking heat out of the system, so as to cool it down. Okay, so it looks like 150 is too much, in fact too low. So we'll probably let this fella iterate a few times to see what happens. That's way lower than what we want. So let's increase the temperature to about 155 and see what happens. So we can always change the parameters as it's doing the recycle. So you don't have to wait for everything to, stop. So, okay, let's see. Oh, so now it's converged at 263. Okay, then the outlet temperature is about 283. So again, that's not exactly what we want. So let's just reduce the temperature a bit more. 154. Okay, it doesn't seem to do that. So let's just delete this. You can see whether we can delete this. And we'll use this as a specification instead. Well, what's the temperature here? 186.5. Let's see whether it works. Okay. And the pressure here is about 7896. Okay, so it doesn't seem to solve. So we have to use the inlet streamway. Okay, you have to use the inlet stream conditions to calculate. So again, let's try and do it a little more systematically. So this should be about 279.6. So let's just use the define from stream function again. So reactor effluent, this should be our 279.6. This should be 160. So let's do a 160 to see what happens. So basically it looks like the heat exchanger area is pretty big. Okay, so what's going on here? There's something plausible that's happening. Okay, besides the computer hanging. So the computer's hanging now, so let's just wait for it to unhang itself before we get back. Okay, so like I said before, right? When you have a heat exchanger, the simple one, so HYSYS will calculate the outlets based on what you specify. Or rather, HYSYS will calculate the UA value. So this Q equals UA, right? So HYSYS will calculate UA value based on outlet streams. So you're asking why isn't it converging the way we want it? So the simple heat exchanger will calculate the UA value, basically the heat exchanger size, based on the outlet streams. So heat exchanger is sized based on specifications. But in the rigorous one, so once you start sizing the rigorous one, so HYSYS actually fixes UA, or rather the area of heat exchanger. So basically this heat exchanger you see here in the center, where the computer's hanging, so that actually was designed for bringing this stream. Okay, let's close the program. Yeah, it was designed for bringing the stream, let's say, from 50 degrees to about 100 and something. So 250. All right. So let's see this one. Okay. Yeah, it was designed to bring it up from 50 degrees to 250 degrees C. So that's what we were sizing it based on. But now we want to just do you want to give it a lighter load, so it's going from 160 all the way up to 250. So the heat transfer rate will be a lot less, and that is what we should be sizing it for. So not to worry, all we need to do to resize is go back to the simple weighted model. We'll just click yes, wait for this fella to unhang itself, and just save it. Yeah, so we need to be going from 160 instead of 50. So let's go for the 160 version instead. 160, and yep, That's what we were aiming for previously. So let's size it based on the 160 model. So HYSYS now auto-calculates some area. So by rigorously sizing, we fix the area of the heat exchanger. So when we press size exchanger auto size, it will size the area of the heat exchanger. So we just do that and let HYSYS solve it again. So let's just press yes. So we close it and it should be able to converge this time. Yep, there you go. Excellent. So what happens? The outlet stream temperature is about 280 degrees C, and here it's about 186.5. Okay, so that actually concludes how we actually should size our heat exchanger. So in summary, this was just an exercise to show you how to actually do the rigorous heat exchanger calculations, and that was based on HYSYS actually fixing the UA for you, and you have to predefine the two inlet conditions before the heat exchanger system will actually solve. And of course, you can actually take a look at what your heat exchanger looks like in this rigorous shell and tube tab, and then it'll give you the tube layout here. You can see this beautiful picture of many tubes here, and the settings plan, etc, etc. So yeah, thanks for watching this introduction to rigorous heat exchanger. Maybe in the next video we'll discuss why the heat exchanger wasn't functioning as it should, and if that was the case, how do we actually convert it into something that is suitable for what we want to use it for. So thanks for watching, guys. We'll see you guys next time. Bye bye.